So, we have done a lot of magnetostatics with steady currents, varieties of currents, straight, long current, solenoid, this, that. Now, recall our lecture 1. In lecture 1, I showed you some demonstrations with bar magnets, and that time we discussed that bar magnet also produces magnetic field, and if the bar magnet is at rest, then this magnetic field is also constant everywhere in time, and it is a magnetostatic field. Now, we come back to this topic, how material, bar magnet is a material, some object made from some ferromagnetic material. How this materials produces magnetic fields. We gave some hints in lecture 1 that every material is made of atoms and each atom has electrons, and it is because of this these electrons that you have some kind of atomic current, and it is this atomic current which is combining in this whole bar magnet or whole material, and then it produces magnetic field. So, we will elaborate on this particular topic in the remaining chapters. Magnetism in materials, you can name it. Okay. So, once again, you have matter, material, matter. So, you have atoms, and in this atoms you have nucleus and electrons. Now, the nucleus has proton and then neutrons and then electrons. Now, it so happens, and this is not classical electromagnetism, it is quantum picture coming in. It so happens that each proton in the world, each electron in the world, each neutron in the world, they have some magnetic dipole moment even without any motion, built in, intrinsic. It is there. If the proton is there, no matter whether you give it a motion or not, whether it is moving or not, this proton, this electron, this neutron, they all have some magnetic dipole moment that we call spin magnetic moment. Okay. It is not a spinning, it is not a spinning because that is a motion. If it spins, that is a motion. Because of motion, there is a current and there is a magnetic dipole moment that is separate. Independent of that, just if the proton exists, if the electron exists, if the neutron exists, the magnetic moment is very much there. So, it is equivalent to a current, but it is built in, it is not external. So, this is an important thing to know, and the magnetic dipole moment of protons and neutrons are very, very small as compared to that of electron, and therefore, we do not talk for the magnetic moment of the nucleus, we only talk in terms of magnetic moment of the electrons. So, because of this spin, because of the property of spin in these electrons, you have a magnetic moment, and that magnetic moment, if you take the z component of that, it will be of this type, E times h cross divided by and 2 times mass of electron. So, we have used m for our magnetic moment. This small m is also used for the mass, but then we can always put this E to tell that this is the mass and this is the magnetic moment. Okay. So, it is this or it is negative. Z component of the magnetic dipole moment corresponding to the spin property of the electron is either this with a plus sign or with a minus sign. Now, you can see that this Planck's constant divided by 2 pi. This h cross, this line is called cross, this line h and then cross. So, this h cross is written for h by 2 pi and h is the Planck's constant. So, you can understand that okay, some quantum mechanics is coming in, then I say that the z component is either this or this, plus or minus or quantized, all those things are there. Nevertheless, for us the important part is it contains a magnetic dipole moment. And on top of that, if the atom, in the atom, electron has some motion in the neighborhood, electron also had some motion in the neighborhood of the nucleus, and because of that motion also there is a current. So, in totality, this dipole moment and dipole moment due to this current, we combine that and we say that each electron in an atom has a magnetic dipole moment and thus can be represented by a current loop, a tiny current loop, very tiny, very tiny. We are replacing or we are seeing this atom itself as equivalent to a current loop. So, the size of the current loop is also atomic, alright. So, very tiny current loop, but each electron in the atom can be seen like that. Now, in an atom you may have many electrons, right, 20 electrons, 40 electrons, 10 electrons, 12 electrons, 17 electrons, you can have many electrons. And then another quantum mechanics comes in, that these electrons prefer pairing. These electrons prefer pairing, that means in that pair, two electrons will have opposite magnetic dipole moments and they will add to 0. So, for example, in 1s you have 2 electrons. These 2 electrons always pair up. The magnetic moment of one and the other will always be opposite to each other, and combined magnetic moment of 1s, 2 electrons of 1s will be 0. Then you will have p and d and all those different electrons. So, by and large electrons prefer pairing, and therefore, it is possible that the whole atom as a whole, taken all the electrons into account, the magnetic dipole moment is 0. Each electron has a magnetic dipole moment, but then it is possible that the atom as a whole does not have a dipole moment, because all these electrons are paired and the dipole moment of one is opposite to the dipole moment of the other, and then each pair has 0 magnetic moment and total atom also has 0 magnetic moment. It is possible. Okay. So, if that is the case, if each atom of the material, of the object, has 0 magnetic dipole moment, such a material is called diamagnetic material. And when I am saying each atom, it is in a slightly broader sense. You may have molecules. So, molecule can also be one unit. So, you have an atom here, you have an atom here, there are some electrons which are shared. So, you do not know whether this electron belongs to this atom or this electron belongs to that atom, but as a whole it is possible that the molecule, which is the unit, or if it is ionic solid, then each ion there. So, each unit as such is neutral, it does not have a magnetic dipole moment. So, if that be the case, then such a material is called diamagnetic material. If that is not the case, this individual units, atoms or molecules or ions, this individual units have magnetic moment, then it is not diamagnetic. There are two categories which we will be talking. But before that, let me define a quantity which will be used in the following lectures, and that is magnetization. Okay. In the normal language, we use this word that this iron nail is magnetized or it is not magnetized and so on, but then this word magnetization is a technical word, has a particular meaning, and the meaning is the following: it is a vector field, it is a vector quantity depending on space points, and it is generally written as, or at least we will write as m vector, capital M vector. And what is this capital M vector? What is this magnetization in the material? For that, it is, you take the object, suppose this is that piece, of material, and then you take some point. So, this is a point, alright, this is a point, some point in the material, and there you construct a small volume, and this volume d tau, this will contain a number of atoms, molecules. So, our d tau is not so small that only 5-6 atoms are there, and it is not very large also, because we would like to differentiate between the magnetization here and magnetization here and magnetization here. So, typically let us say micrometer cubes or so, so that you have thousands and thousands of atoms here, large number as such, but not necessarily 1 centimeter cube type of volume, still a small volume. And then ask, what is the total magnetic dipole moment of all the atoms taken together here? These all atoms in this d tau, how much is the total magnetic dipole moment of all these atoms which are there, all whatever. When I say atoms, you understand that I am talking of atoms, molecules, ions, whatever the structure of the material according to that. So, that net magnetic moment of this d tau, magnetic dipole moment, that you look at and then divide by this d tau. So, it is magnetic dipole moment divided by the volume d tau. This quantity, it will have a direction, you know, magnetic dipole moment has a direction. So, when you add up all the magnetic moments of all the atoms, it will have some direction, some magnitude. So, look at that magnetic dipole moment of this part divided by this volume, and that is known as magnetization of this material at this point. At different points it can be different. Here, if you take point here and then construct a similar small volume, then maybe this total magnetic moment is different from this, or maybe it is equal. So, in general it will vary, and this is known as magnetization. So, for a diamagnetic material, this M is intrinsically 0, just the material is there, nothing around, which can affect it, this magnetization is 0, because each atom has 0 magnetic moment. So when you combine all those atomic dipole moments, you are going to get 0. So it is 0. What happens if this material is suddenly put in a magnetic field, or we bring in a magnetic field there, right? Around this material there is no magnetic field to start with, but now we bring in the magnetic field there, we switch on a magnetic field. What will happen? So we can use our high school knowledge once again, although it is not magnetostatics, it is dynamics, Faraday's law, and maybe in the third course on this classical electromagnetism we will talk more about it. But then you know that if there is a loop, and then the magnetic field is increased, some magnetic field is there going through this, and if this magnetic field, you define flux of this magnetic field on the area bounded by the loop, okay, and if this flux changes with time, then this minus d phi dt is known as the EMF produced. A changing magnetic field will produce an EMF. If this magnetic field is changing, or this is creating something, we will talk more on that later sometime. But then an EMF is produced, and then there, if possible, if the charges are there, then a current is induced. So if I just use that, and suppose I have an atom, consider just one electron of that electron is equivalent to a current loop. So it is going in a loop, this electron is going in a loop. So there is an electron, okay, there is a current, there is a possibility of current, depending on how fast it is going and what is the radius and so on and so forth. There is a current, all equivalent pictures. Electrons are much more dramatic than this simple picture of going along a circle or so, but it is a good equivalent picture for some of the applications. All right. So the current is there, the charges are there, the loop is there, and it can move in this. Now if this magnetic field was 0 to start with, and then we switched on the magnetic field, so we have increased the magnetic field from 0, we have increased the magnetic field, and therefore an extra current will be induced. Whatever its motion was there and current was there, magnetic dipole moment was there, it was there, but because of this EMF, an extra current will be induced, and then you can see that this extra current should produce its own magnetic field in opposite direction, right. This is the magnetic field that we applied, and this is the magnetic field I am talking of, which is produced by this extra current induced because of this flux change, because of this change in B, and that should produce a magnetic field in the downward direction. And that means with that extra current, which is flowing extra current, if you write magnetic dipole corresponding to that, magnetic dipole moment corresponding to that, then that should be in this direction. This is the induced magnetic dipole moment. And that means if you apply a magnetic field, you create an extra magnetic moment, dipole moment, and that is in the opposite direction. So, if you, and the other pair also, it does not depend whether initial current is this way or that way, that initial current is there, that initial dipole moment is there. This is the extra one which is coming from this B, which is suddenly switched on. So, if you have paired electrons, in which one dipole moment was in upward direction, then other was in downward direction, the total was 0. But for both these electrons, when this magnetic field is switched on, this extra magnetic dipole moment is created in the downward direction, and therefore the total, which was 0, now it will be in the direction opposite to the magnetic field. So, that means a magnetization is now produced. There was no magnetization in the material, there was no magnetization in the diamagnetic material, but if you put it in a magnetic field, then a magnetization will appear, and that magnetization will be in the direction opposite to the applied magnetic field. So, this is the property of diamagnetic materials. Now, this property has a very interesting effect that you can just do an experiment and see there, and that is, suppose you have this small part of this diamagnetic material, and we have applied magnetic field in this direction like this. This can be produced by a magnet. This kind of magnetic field can be produced by a magnet, a permanent magnet here, and here is that diamagnetic material. So, because of this, a dipole moment is produced in this direction, right. In this, there was no dipole moment to start with, but now there is a dipole moment in this direction opposite to the applied magnetic field. Now, a magnetic dipole, so it is essentially equivalent to a current, and that current is current loop is giving me this magnetic dipole moment. But then remember, in one of the lectures we said that for many of the cases you can do a very simple modeling, mathematical modeling. It's far from reality, but it gives the correct mathematics, and that was introducing magnetic charges plus qm and minus qm. All right. So, go back to a few lectures ago, we did that if the magnetic moment is in this direction, that means there is equivalently this whole object, small object here, equivalently you can write it as a current loop, and looking from this side it should be anticlockwise, and then this is the dipole moment. But then this can be replaced for our mathematical purposes by a combination of 2 points, one having magnetic charge minus qm, another having magnetic charge plus qm, and the same electric dipole type formula can be used to write the dipole moment qm times d. And in this picture we said that the force, if there is a magnetic field, the force by the magnetic field will be qm times b. So, if this is positive charge, then the force on this magnetic charge here will be qm times b, and if it is negative, then the force will be opposite to b. So, this is our mathematical modeling, and with this we try to write the magnetic dipole moment of a current loop in the plane of the loop. On the axis it is easy. On the axis, writing magnetic field here, because of this current loop on the axis is easy. You can do, we have done it, you can integrate the things and you get an answer. But in the plane, there this integration will be very difficult, or closed form integration will not be perhaps possible. But then if I say that okay, this is equivalent to a a minus qm plus qm, then it's very simple. You know there is end on position, there is broadside on position, and using these things, using that the field produced by qm is mu naught over 4 pi and then qm by r square in that radial direction. You can easily write the equation for the field here. So, for many of the applications it works. Here also we can do that, here also we can do that. This magnetic dipole moment which is induced due to this magnetic field, you can write this as, you can replace this as a this direction. So, a minus qm here and a plus qm here. What is the force on this plus qm? Force on plus qm, it is qm times b. B here at this point, b here, let me call it b1, because it's magnet and the magnetic field is varying, it is getting weaker as you go ahead. Which direction? Towards right in the picture. And what is the force on minus qm? It is again qm times the magnetic field, and that is b2. Here is minus qm, and here the magnetic field is b2. Here the magnetic field is b1. I am writing b1, b2 because they are not equal. This b1 is larger, closer to the magnet. This b2 is smaller, is farther away from the magnet. So, it is this, and it is a negative magnetic charge that we have assumed, and therefore, the force is towards left. Right, the force is towards left. What is the net force? Net force by the magnetic field on the object. What will be the direction? I am interested in direction essentially. This is closer to the magnet. So, this B1 is larger. So, this is larger towards right, and towards left this is smaller in magnitude, and therefore, when you combine you will get a net force towards right. Net force by the magnetic field on the object is towards right, with some magnitude that will be this QMB2 minus QMB1 minus QMB2, that will be the magnitude. But the essential point I want to bring from this discussion is that when you bring a diamagnetic material close to a magnet, the magnet repels it. Initially it was unmagnetized. Our nail, iron nail, is also initially unmagnetized, but when we bring a magnet close to it, right, this is the iron nail, let us say this is the iron nail, and then if this is magnet, invariably the iron nail is attracted towards the magnet. Initially this was also unmagnetized, but then because of this magnetic field, it gets magnetized, it gets a net dipole moment. It is not a diamagnetic material, but still, to start with, this whole thing is unmagnetized. We will talk about that next lecture, but then it is attracted. But this object, which is also unmagnetized, when this is brought close to the magnet, it repels. So, many of the, or rather all the things that we see on the earth's surface, 6,400 kilometers radius, all the things that we have at the surface of the earth, some 70-80% of that is diamagnetic. is diamagnetic because water is diamagnetic. And you know, if you see that picture of Earth taken from satellites, it's all blue, 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 and this entire blue is water, right? So you have water in great abundance, and water is diamagnetic. There are many other materials. Copper is also diamagnetic. So next lecture we will show you an experiment, and this diamagnetic property of water, our most familiar, most useful, most necessary object on the earth for life, we will show you that yes, water is diamagnetic, it is repelled by a magnet, and then we will talk about other kinds of materials.